My name is Eyal, and I've been working with software for more than 2 decades now. The last 6 or 7 years, I've been working with Python and SaaS applications, and lately I'm working in Scenario. I lead the data team. In Scenario, what we do is we secure hospitals. So if you guys are from a hospital, you can raise your hand and join me later. Okay? So today I'm going to talk about a journey we had to accommodate around 100,000 events in our data system. But, you know, a journey, this is not about the journey. It's about the lessons we learned on the way. So I'm going to try and start from the beginning. So maybe not the beginning, but a beginning. So what do we do in Scenario? So what we do is we give hospitals a server to have in their system, and then we collect data from that server, all the metadata on the network traffic, and then we try to help them improve their security. So how do we do it? So first of all, we detect the devices and identify them. Then we understand the security status of each of the devices. And then we give recommendations. We give recommendations how they can improve their security and what they can do to help improve what they're currently doing. Today I'm going to focus on how we detect devices and identify them. Okay, so let's try and see an example. So assuming we have a device talking to another device in HTTP protocol, so you would see the path that is sent and the type of method. And here you can see that the device is asking for an MRI-related data pass. And then you can see another request from another server to the same device. This is a DICOM protocol. So DICOM is a medical-related protocol for modalities. And this is for requesting a file from the server. So what can you conclude from this? So if you run some kind of classification algorithm, you can conclude this is a PAX server. What is a PAX server? So it's a file storage server. So this, if you look at the traffic through time, then you can run a classification algorithms and determine the types and properties of the devices. So this is what we do. We collect the data from the different hospitals. We then process them to extract information from the network traffic. We store the data into a database and then run batch processing for classification and categorization to understand what kind of devices we have. The focus of this presentation is this database. So what's important for it? It's important. The important part is that it receives information from all the hospitals, and then later on, all the information is collected in batch processes and handled together. So our first stop. So first we started with Redis. So you probably know Redis. Redis is in-memory data storage. It supports various data types because it's NoSQL data storage. You can store strings and hashes and lists. And it's known for high performance and low latency. So why do we do it? We thought about Redis because we already had Redis in our system. It's easy to deploy. We had it, you can have it as a managed service in your cloud provider. And of course, because it's NoSQL, so you don't need migrations to change the data structures. You just change your format of key and values, and you can easily get whatever you want from it. So it was a start, and it was a low-touch infrastructure, so we decided this is a good start. So we started with this schema. So the schema represents each attribute we want to save with the value, and the last time we saw it. So we can then filter, when we do the batch processing, we can iterate over all the values and drop those that are too late backwards in time. So that was nice. We started with this client, so we do a set each time we want to store something, and then we retrieve using get and in the batch processing. But what's the problem with this simplistic client? So first of all, every new set and new get, you need to run to the server and backwards. So you have a round trip. Using async IO as I did before helps. So you can batch the IO into a specific part and help your processors work better. But still, a round trip for each request is quite a large overhead. So we thought maybe we'd use pipes. I don't know if you know pipes, but pipes is a Redis structure that helps you batch requests together into a single round trip to the server. So this is how you set into the pipe locally. And then there's the part where you decide when you want to run the actual round trip to the server. We have here a time constraint and a size constraint. And then you just execute, and then the data is transferred to the system. So this is nice. This solves the first part where you need to run for each set to the server. But when you do retrieve that information, you still have to iterate over and do a get per item. So Redis also has set attributes, which are batching of multiple values into a single item. So you can use sets and pipes together. Here you can see that. Sorry. You can see the pipe add, sadd instead of set, and then when you retrieve, you get all the S members. So this is a good solution for storing all this. So what was the outcome? Sorry. So we did this, and it actually reduced the I/O costs for the set and get, and the system was able to handle a few thousand requests. But this was a bit low. We needed more for our system. And because Redis was single-threaded, collection time was still very, very slow. Okay, because we needed to wait for the sets to end and then retrieve. And also, we tried scaling. So we scaled the database, we scaled the workers, but still we couldn't get to the scale we wanted. So we had to move on. We moved on to timescale. Timescale is a time series database. It's based on Postgres. It extends Postgres with a time series features like partitioning, automatic partitioning, continuous aggregations, and hypertables. It's designed for high scale performance, and you can use SQL to query it. So why do we think that timescale was a good option? So we could use the raw tables, so we could investigate backwards our information. And also we used aggregation policies to aggregate the data from the raw tables into the output batch processing format without intervention and additional queries. And also we used partitioning. So partitioning helps you separate different time frames and different customers, so the database could optimize the CPU well. And also it really helped that timescale uses SQL, because our analysts, they use SQL, and we could let them use this database to retrieve the information they needed. So this is how a timescale database, the raw table looks like. First, you have the table definition itself. You have the specific fields, and then you create a hypertable. Hypertable is how you separate the data into partitions. So here we partition it according to customer and according to time. So each 3 hours you get a new partition, and then the database can work in parallel on multiple partitions when you query it. Okay, so this helps you get better performance from the same database. Then you have the storage policies. So there are two types of storage policies. There's a compression policy, which helps you optimize the storage size. And then there's retention policies, which helps you utilize your disk better, because you don't usually need all the data from all the time backwards. So the database helps you handle this swiftly. This is how an aggregated table looks like. So first of all, there's the query itself of how you aggregate. So for here, we used the max last seen. So you want the last appearance of each of the values. So again, this is very similar to what we had in Redis. We store per item the last time we saw it. Sorry. And here you decide how you want to aggregate. You aggregate it by buckets, by day. So this is how the group by works. And last, you have the continuous aggregation functionality. You define when the database runs the aggregation. So it runs it every hour, and the data that it looks into is 1 day backward until 2 day backwards. So you have the information you want and need according to what your use case is. If you look at how a client is implemented, so this is a very simple async PG. I don't know if you guys use Postgres, but this is very simple. Okay, very similar to what Postgres clients look like. The only main difference here is that we use batching again to avoid the need to use round trips every request to the server. And here too, you can see how we batch according to time and to the buffer size. And specifically here, what we do is we use active buffer and inactive buffer to avoid the need to wait for writing to the database when inserting into when using the client to insert. When you look at how the aggregation function the side of the aggregation looks like, so it's a simple query. It just runs on the aggregation table, and you query whatever you need in order to, oh, sorry, this is the insert. Oh, so you just insert in the table without worrying about what you do in the aggregation part. When you look at what happens when you want to use it, you just connect to the database, you do your workload, and when the service is done, you can disconnect from the database. So a nice tweak on this is having async context manager. So if you define async context manager, you don't have to worry about cleanup of the database. So you can just ignore handling what happens during exceptions and during involuntary exits of the service. The resources are cleaned automatically. So when you want to use the aggregation query, as I said before, you can just query. This is very simple. You just query the aggregated table, and this is without any considerations about where you inserted the data into, because the database itself handles the conversion between the raw table and the aggregated table. So where did this take us? So when the system was up to 30,000 events, this worked okay. Inserts went in correctly, and we were able to query the database with good enough performance. But when the system grew and more customers joined our system, it started to shake. So when we reached 100,000 events per second, inserts started dropping, and the query for aggregating the data reached several hours, and we were not able to use this as a solution. So we had to move on. Where do we move on? So the last stop is ClickHouse. I don't know if you know ClickHouse. ClickHouse is an OLAP database. It's a high-performance analytical. It does high-performance analytical queries, and it provides fast processing and efficient storage and compression. Why did we use ClickHouse? So we wanted to try an OLAP database, and there are many vendors of OLAP databases. There's Snowflake, and there's vendor-specific like Google BigQuery, but we wanted something that's cloud agnostic, and also we looked at the pricing, and ClickHouse gave a competitive pricing approach. So we decided to do a POC and test it. So we tested the insert rates, and it worked. And we saw that the query time was significantly better than what we expected. And also, the format that ClickHouse used was very similar to what we did in the aggregation queries in timescale. So we thought this would be an advantage in the migration between the two coding frameworks. And so also we saw that the cost estimations were lower than what we paid before. So that was a very good point in getting a buy-in from our organization. Sorry. So how does a schema look like? So in ClickHouse, what you define the aggregation table itself as a simple aggregation. Here you can see again the max on the last scene. What you define next is how you partition the table. Before we saw that we had a 3-hour partition, and now we have a monthly partition because ClickHouse supports much larger partitions to work well. And then we have the storage policy. The storage policy defines where and how ClickHouse stores the data inside your system. And last, you have how the data is split between the different clusters. So ClickHouse is a multi-cluster environment. So data, what you need to remember is that you want the data split as evenly as possible between the different clusters to leverage the compute power of each of the cluster members. This is how the storage policy looks like, but I'm really not going into this. What I will show you is this is how it actually works. So what we have is we have a local SSD on the ClickHouse server, and we move from the SSD to an S3 storage due to two considerations. One is time considerations, because we want to store only new information that is being handled by the cluster and being merged inside the cluster, and thus handled with high compute and a lot of processing and changes. And then when the data is stable and a few days old, we move it to S3 for cost considerations. The second part is that when the data is, there's no more space left on the device, we want S3 as a backup for this system. Okay? So a ClickHouse client is very similar to what you expect from a database client. It's just a simple wrapper over the library. What's nice and what we did here is that we used a wrapper over the extension of the library itself to have retries. We used Tenacity library. So I don't know if you've seen this library, but it really helps you remove boilerplate and clean up your code for error handling, logging, and retries on your code. Again, we used a bulk insert client. You can notice here that the batch sizes are much larger because here again, ClickHouse supports much larger partitions. And this is one of the ways you need to tweak when you move between different databases. You need to understand the trade-offs between having larger partitions, larger insert rates, and the performance the database will perform with this. When we look at the flush, so it's very similar to what we saw before. You have the execute itself, and then wrapped over with a should flush that inserts the batch size and the time constraints. What were the outcomes? So we saw that there were no more insert drops. Also, we saw that the query time was decreased into 30 seconds, and instead of 2 timescale servers, we used a single ClickHouse server. Also, because we saw that database utilization was around 40%, we understood that there was much space to grow to, and we were quite happy with this. The only main issue is that when we exported from this database, the export process itself consumed a lot of memory on each of the clusters. And in order to avoid out-of-memory problems, we partitioned the query into smaller parts and then run each of the parts iteratively. So what's next? I don't know, but there'll probably be a next hop. Currently, we're handling more than 150,000 events per second. We're quite pleased with ClickHouse, and we're adding more and more flows into this framework. What did we learn? So first of all, we learned that Python, although it's a slower language, can actually handle this kind of weight. So you can handle hundreds of thousands of events per second with Python. And it's just about finding the right tools. So I don't know if these considerations are your considerations, but this is something you need to find for yourself, the tools that are relevant for your tasks. The second part is that you need to separate processing and ingestion. So because processing requires high CPU and ingestion usually requires memory, you can separate the pods to different pods and have pods with higher CPU and pods with higher memory, and this will help you scale your system much better. A third thing we learned is that when you batch I/O, you can perform much better. So you need to batch your I/O and then run it together to get the best performance from your systems. And last, and also least, so having small code structures like tenacity or context managers helps you clean your code, helps you make your code cleaner and better and more understandable, and this is something that's very important when you handle a large system. So here's a table that I created that sums up all the things that I talked about. You can have it later in the presentation. Thank you very much. I'm available at eyal@gmail.com or eyal@scenario. All the code in this is available in the GitHub repo. Thank you. Any questions? Yeah.
Yeah, I want to ask, what did you use to measure how much time it takes, or how you handle the requests?
So we have the data stored into our queuing system, and we see the throughput of retrieval of information from our queuing system. This is the main metric. And also we use Prometheus and metrics in general to measure stuff. So we have measurements over per message, per batch, per everything. Anything else? Thank you guys very much.